So in this chapter, we want to look at some early atomic theories and see how the structure of the atom was discovered. The reason this is important is because remember we defined atoms as the fundamental particle of the matter, and we define atoms as particles that cannot be broken into anything smaller. So since matter is composed of atoms, it's very important for us to know exactly what the structure of the atom is. Once we know the structure of the atom, then we can explore the reactions and we can invent and explore. So we want to look at the structure of the atom, see what atoms are composed of. So subatomic particles, we're going to learn about electrons, protons, and neutrons. And then we give you a very brief description of what each particle is and how we can find the number of them and how they're arranged around the atom. And then we'll talk about the isotopes and some atomic masses. Now, for this chapter, you're going to need your periodic tables. Get your periodic tables out. We're going to learn how to find the number of subatomic particles. Part of it from the periodic table and part of it is by calculations. So in your textbook, you have a good review of the early atomic theories. I suggest that you review the early atomic theories, see how the idea started, and for now, we're just gonna focus on the more the subatomic particles and not much the history. So as we said, matter is composed of atoms. Atoms are the fundamental particle of the matter that they cannot be broken into anything smaller. So this also shows the picture of the atoms. This is the scanning electron microscopy picture of some atoms. And atoms, keep in mind that the atoms are extremely small. The diameter of a single atom is between 0.1 to 0.5 nanometers. And remember that nano is a very small unit. So basically this is 0.1 times 10 to the negative 9 to 0.5 times 10 to the negative 9 meter. And as you see, this is very small. Now, so how these subatomic particles were discovered is that actually the first subatomic particle that was discovered were the electrons. And it was believed that electrons have negative charges. So the symbol for the electron and the charge is given to you here. And by different experiments, scientists were also able to find the size, the mass of the electron, and also the size of the electron. So the mass and size of the electron you don't need to memorize. You need to know that electrons have a negative charge. That's the only one you require to memorize. But I'm going to show you the mass and size of electron, protons, and neutrons. You don't need to memorize the actual numbers. But what I want you to look at is the size and get a sense of how small these subatomic particles are. Now, the first subatomic particle that was discovered were the electrons. Scientists knew that atoms were neutral. So since electrons were discovered and they knew that electrons have a negative charge, they concluded that there has to be other particles, subatomic particles, that have a positive charge. That way the atom can be neutral. So electrons, they have a negative charge. We know how many of them we have. And then we have protons who have a positive charge. And then for a neutral atom, neutral meaning no charge, the number of protons have to equal to the number of electrons. So the existence of protons were sort of discovered indirectly. So electrons, they have a negative charge, and protons, they have a positive charge. And we know that for a neutral atom, the number of protons equals to the number of electrons. Now, scientists also discovered another subatomic particle, which were the neutrons. Neutrons do not have any charge on them. Neutrons, no charge, they're neutral. However, they add up to the mass of the atom. So towards the end of this chapter, we talk about isotopes, and I show you how neutrons were discovered, and I show you where they exist and how they add up to the mass of the atom. So 3 subatomic particles we need to know for this class: electrons, protons, and neutrons. Make sure you know what the symbol for electron, protons, and neutrons are, and also you need to know the charges for electron, protons, and neutrons. Now, what we want to show you is that the chemical properties of the atom can be described based on the number of electrons, protons, and neutrons. What's important is the number of electrons, protons, and neutrons, and we're going to learn later on that the location of the electrons become very, very important when we talk about, bonding and chemical reactions. So for now, we're going to learn how to count the number of electrons, protons, and neutrons. We're going to learn the basic structure of the atom, know where electrons are, protons, and neutrons, where they reside in the structure of the atom. And in the chapters later on, we're going to learn how the number and the location of the electrons affect the properties and reactions of different atoms. Now, keep in mind that in the structure of the atom, what we believe, the simplest way we can tell how the atom looks like is that in the center of the atom, there is the nucleus. Nucleus is very tiny and it's very dense. Inside the nucleus are the protons and neutrons. And nucleus is dense just because we have neutrons in there. Remember that neutrons, they have a mass. Now, we also believe that there are orbits around the nucleus. Electrons spin around the nucleus. So the nucleus has a positive charge because protons are inside the nucleus. And then the electrons, they have a negative charge. Now, one thing to know and keep in mind for now until we learn more theory about the structure of the atom is that when atoms interact with each other, form bond or go through interactions, the atoms basically get close to each other. Once they get close to each other, the electrons are the subatomic particles of the atoms that come into contact with each other. So when bonding is formed, when new materials are formed, those are from the interaction of the electrons. So most chemical reactions, formation of ions, is done through the transfer of the electrons. Why electrons? Because if you look at the structure of the atom, electrons are the subatomic particle that are actually accessible, available. These are the outermost subatomic particles. So the first subatomic particles that are going to interact with each other are going to be electrons. The nucleus is in the center of the atom. It's shielded by those electrons that are around it, meaning that neutrons or protons don't undergo chemical reactions that easily. It doesn't mean that it's impossible to change the number of protons in the nucleus. It is possible, but it is hard. So anything in chemistry that deals with the change in the nucleus. Number of protons and number of neutrons becomes nuclear chemistry. Nuclear chemistry, we don't talk about it in this class. But anything that involves the transfer of electrons, the change in the number of electrons, the interaction in between the electrons, that's we basically cover in chemistry, in this class, in Gen Chem. Now, since nucleus is in the center of the atom, and I just said that nucleus is very small, very dense, and it's hard to even get to the nucleus and make changes in the number of protons and neutrons. The number of neutrons will actually define what type of element you have. The number of neutrons for each element is called the atomic number. So the atomic number is the number of protons. So atomic number is the one thing that can identify your element completely. So if you know how many protons you have, you can tell exactly what element you have. And that's the one thing that we don't need to, confirm. For any other characterization technique, we have to do multiple experiments, multiple, characterization technique to prove or to figure out what we have. But number of protons, since it doesn't change, is the one thing that can tell you for sure 100% what type of element you have. It can tell you the identity of your element. Now, one thing to pay attention to here is that if the number of protons change, the type of element, the identity of the element is going to change. Now, in the periodic table, we can find the number of protons for each element. So if you look at your periodic tables, in each box where you have the symbol of the element, there is a number on top of each box. That number represents the number of protons, and that number is the atomic number. So the atomic number which is the number of protons we can find it from the periodic table. So let's say found in the periodic table. So we learned how to find the number of one subatomic particle, which is the protons from the periodic table. And then again, remember that's the number that comes on the top of each box. And also, if you look at your periodic tables, you should notice that the elements in the periodic table are arranged based on the increasing of the atomic number. So you start with the hydrogen atom, which the atomic number is 1. Atomic number means the number of proton, and then to helium. And the elements in the periodic table are arranged based on the increasing of the atomic number. Now let's look at the periodic table and do a little bit of practice here. So what's the name of the element with atomic number 14? Silicon. Very good. So how many protons for silicon? 14. How many electrons for silicon? 14. Why is it 14 electrons for silicon? Very good. So for any neutral element, neutral meaning that no charge, number of electrons equals to the number of protons. Now in the periodic table, if you look at silicon, there is no charge on the silicon. So the number of electrons equals to the number of protons. The number of electrons, remember, we can't find that from the periodic table. However, the number of protons we can find from the periodic table. So 14 protons for silicon, and since it's neutral, the number of electrons should equal to the number of protons. That means 14 electrons for silicon as well. So far, we learned about two subatomic particles, protons and electrons, and we learned how to count the number of protons and electrons for a neutral atom. So for the protons, that's the atomic number. We look at the periodic table, and if the atom element is neutral, the number of electrons equals to the number of protons. Now, there is another subatomic particle, neutron, that I showed you earlier. Neutron with the protons, they reside in the nucleus. And neutrons don't have a charge, but they have a mass. So how neutrons were discovered was that scientists discovered elements that had the same number of protons, but they didn't have the same mass. Since they didn't have the same mass, scientists concluded that there should be another particle in the atom that has no charge, but it only adds up to the mass of the atom. So they call that neutrons, and they discovered that neutrons basically reside in the nucleus with the protons. Now, those type of elements that have the same number of protons, meaning the same atomic number, but different mass, are called isotopes. So isotopes, they have the same atomic number, same number of protons. So atomic number, meaning that same number of protons, but they have different number of neutrons. So here I want to show you an example of isotopes. So on this slide, you see three different isotopes of hydrogen atom. So hydrogen 1, hydrogen 2, and hydrogen 3. So hydrogen 1, it has 1 protons and 0 neutrons. But there is an isotope of hydrogen, which we show that with D, it's called deuterium, which has 1 proton, same number of protons because it's a hydrogen atom, but it has 1 neutron. There is also another isotope of hydrogen, which is called tritium. It still has 1 proton because it's still hydrogen, except that it has 2 neutrons. So all these 3 nuclei are hydrogen atoms. So they have the same number of protons. They have only 1 proton, which makes them a hydrogen, but they have different number of neutrons. So how do we distinguish in between different isotopes? So for example, if you look at the periodic table now, there is only 1 hydrogen atom, right? We don't see all 3 isotopes of hydrogen. So first of all, in the periodic table, we don't see the different isotopes. To find the isotopes, we need a little bit more information. But we have to have a way to distinguish in between different isotopes. So for different isotopes, we use isotopic notation to show the number of protons and neutrons for each isotope. So in isotopic notation, A, here, this represents the mass number. So the mass number for each isotope goes on the top left corner or right corner of the symbol. And mass number represents the number of protons plus neutrons. You gotta memorize how to find the mass number. And isotopic notation, you gotta memorize where atomic number and mass number goes to. So mass number, which goes on the top for isotopes, that represents the number of protons plus neutrons. an atomic number on the bottom that represents the number of protons. So if we have the mass number for any isotope, we should be able to find the number of protons and neutrons for each one of the elements. Now, if you look at the isotopic notations for the 3 isotopes of hydrogen, these are all isotopic notations for all 3 isotopes of hydrogen. Now, we read the isotopes with their mass number. So, for example, the protium, when I read this as hydrogen 1. Deuterium, I read it as hydrogen 2. And tritium, I read it as hydrogen 3. So this is how we read the isotopes, and we distinguish in between the isotopes. So let's practice and see how we can find the number of electrons, protons, and neutrons. So let's look at copper 64. So just the way it's written, it tells me that it's an isotope of copper. It tells me that copper has different isotopes, and I read it as copper 64. And we want to know how many protons, electrons, and neutrons this isotope of copper has. Now, 64 represents the mass number. So based on the isotopic notation, I know that 64 represents the mass number, and 29 obviously represents the atomic number. So atomic number is 29. How many protons do you expect in the copper atom? Very good. So atomic number represents the number of protons. So atomic number 29 tells me that there are 29 protons in copper. Now we still have to find the number of neutrons for copper. So remember that mass number is the number of protons plus number of neutrons. So mass number is 64. So if mass number is 64, we have the number of protons, which is 29. That gives us 35 neutrons for this isotope of copper. How many electrons does this isotope of copper have? How many electrons for this isotope of copper? Very good. It also has 29 electrons. Why? Because this isotope of copper is neutral. I don't see any charge on it. So it's neutral. Since it's neutral, the number of protons equals to the number of electrons. So you would expect 29 electrons for this isotope of copper as well. So we can basically count the number of electrons, protons, and neutrons. For now, we're just learning how to count the number of electrons, protons, and neutrons. Later on, we learn the application. We're going to see why these number of electrons, protons, and neutrons are important. So let's look at an example. You want to know which isotope corresponds to an element with 24 protons and 28 neutrons. So we want to find an isotope where the number of protons are 24 and the number of neutrons is 28. So let's see first of all what atom we're looking at. So 24 protons, I'm going to look at the periodic table because the number of protons represents the atomic number. So 24 in the periodic table represents chromium. So I know that it's not nickel, tellurium. Oh, this chromium could be an option too. So 24 protons means that we're dealing with basically chromium. And since it is 24 protons, the atomic number, we know that it goes on the bottom here. Now to find the mass number, A, which represents mass number, is the number of protons plus the number of neutrons, which is 52. So this represents the isotopic notation for chromium with 28 neutrons. So the answer would be B. So now we've been talking about isotopes and saying how the difference in the number of neutrons affects the mass of each isotope. So let's look at the atomic mass and see how the masses of each isotope are going to be different. And since the elements that have isotopes, they have different masses for each isotope, we want to learn how we can find the average atomic mass for each element. Now, the unit that's used for the atomic mass is AMU. And one AMU is defined as 1.66 times 10 to the negative 24th gram. Now, the atomic masses of the element are all calculated with reference to carbon-12, the isotope of carbon, which is carbon-12, that is the most abundant isotope of carbon. So the atomic masses for the elements in the periodic table, they are relevant to carbon-12. So we're going to learn how to find the atomic mass for each isotope. So why is this important for us to know how to find the atomic mass and also for each isotope and the average atomic mass is, I think I mentioned this earlier, that if you look at the periodic table, in the periodic table we don't see the different isotopes of each element, we only see one. Now, one thing to keep in mind is that these elements that are found in nature, they always come, the ones that have isotopes, they always come as a mixture of different isotopes. So, for example, hydrogen, we just saw that hydrogen has 3 isotopes. So if I get a sample of hydrogen from this room, from outside, or a gas tank, that sample includes all different isotopes of hydrogen. So when we look at a sample of hydrogen, we have to look at the average atomic mass of all 3 isotopes of hydrogen. Also keep in mind that it is possible to have only one isotope of each element, but it depends on how stable that isotope is. So all these atomic masses that come in the periodic table, we want to see how we can find the average atomic mass of the isotopes, and these are for the elements that actually have isotopes. So for example, copper is another example of different isotopes. We have 2 copper 63 and copper 65. Now The atomic mass of copper is 63.54. But each isotope of copper has a different mass. So how do we find out the average atomic mass of copper? So to find the average atomic mass of each element, two things we need to consider. First of all, we need to know how many isotopes each element has. The number of isotopes are important. And also we want to know how abundant each isotope is. Abundant meaning that what's the percentage? Which isotope is more stable? The isotope that's more stable is more abundant. So for example, for the copper 63 and copper 65, on this table you see the abundance for these two. So copper 63 is 69.9% abundant. And copper 65 is only 30%, almost 39% abundant. Meaning that if I get a random sample of copper, in that sample, 69% is copper 63, and the rest of it is going to be copper 65. Now, what's important is that the mass, isotopic mass of each isotope of copper is different. So to find the average atomic mass, we have to take into account the isotopic mass of each isotope and also percent abundance. The isotope that's more abundant is going to contribute more to the average atomic mass of our isotope, of our element. So how do we find the average atomic mass for an isotope? This is the formula. You get the atomic mass of each isotope multiplied by the percent abundance. So since copper has only two isotopes, we do this 2 times. The average atomic mass of the copper 63 multiplied by the percent abundance of copper 63 plus isotopic mass of copper 65 multiplied by the percent abundance of copper 65. Now the unit for the average atomic mass is in AMU. So a couple of things to keep in mind when you look at the average atomic mass. Keep in mind that although it's called average, it's not like taking average, like, you know, adding up and dividing by the number of whatever you're doing. So keep in mind that it is called the average atomic mass of the isotope, but the formula is the atomic mass times percent abundance for the average atomic mass of the isotope. When you do the calculations, keep all the decimal places that are given to you. You look at the significant figures only once at the very end. And also keep in mind that this is the percent abundance, meaning that the abundance that's given to you divided by 100. So 69.09% is 0.6909. 30.9% is 0.3091. For examples, silver exists as 2 isotopes with atomic masses of 106.9041 and 108.9047 AMU. You want to find the average atomic mass of silver if the percent abundance for each isotope is 51.82 and 48.18% respectively. So to find the average atomic mass, that equals to the atomic mass, so 106 0.9041 times percent abundance, which is 51.82 plus the second isotope 108.9047 AMU times percent abundance, which is 4880. So use your calculators and find the average atomic mass of silver. Now, in terms of significant figures, we don't want to round too much. We want to round only one at the end. Now, since you're doing an addition, what's important is the number of decimal points. So each one of the quantities given to us in our formula has 4 decimal points. So I want to keep 8, 6, 7, and 9 up to here. So you can actually round this to 107.8680 AMU. Oops. Now look at the periodic table. Let's find silver in the periodic table. Silver is element 47. And let's look at the atomic mass that's given for silver. So the number that on the bottom of each box that represents the atomic mass. So if you look at the atomic mass of silver that's given in the periodic table, depending on how many decimal points, it's 107.87, I believe, if you round it to 2 decimal points, which matches the average atomic mass of silver. Now, if you look at the atomic masses of each isotope of silver, one is 106, the other one is 108. You see how the average atomic mass doesn't match the mass of each isotope. So it's basically the mass of each isotope times the percent abundance that gives you the average atomic mass. So let's do one more example. Chlorine exists as 2 isotopes, chlorine 37 and chlorine 35. If the percent abundance of each isotope is 24.47% and 75.53%, what is the atomic mass of chlorine 35 if the average atomic mass is 35.46 AMU? So the average atomic mass is 35.46 AMU. So 35.46 AMU. So chlorine 37, we have 2 isotopes. Chlorine 37 is 36.96.590 AMU times percent abundance, which is 0.2447, plus the average atomic mass of chlorine 35, that's what we're solving for, times the percent abundance, which is 53. Now 35.46 AMU equals to, so 36.96. So that's 9.0455 AMU plus 0.7553x, and from here x is 34.96885, and the unit is AMU.